Hey, physical science students, it's Mr. Lambert here. This video for this week is going to be a little bit different because we're trying to get a bunch of information out to you that deals with electromagnetic waves. And I just realized, even though we pushed out the text to you, that if I read a book, a copyrighted book, even on YouTube, show you the pages, it's actually a violation of copyright law. So I don't want to get in trouble. I probably wouldn't, but you're not going to see my voice. I'm not going to show you the pages of the book, but I want to show you where they are. For my physical science class, this is in my Google Classroom. It's in the classwork section. We are in lesson 14, chapter 11. I have Miss Wood's block 1 classwork section up. Notice this is Miss Wood's class. She also has lesson 14, chapter 11, and there's the textbook. So I'm just going to talk real quickly using my computer screen about electromagnetic waves. It starts on page 338 of the book. What are electromagnetic waves? As you can see, I have some Google images here, which I'm allowed to show you. There are a bunch of images here. A lot of them look similar. I would say this one's probably most similar to what's in your book on page 340. But what is an electromagnetic wave? Last unit, we talked about waves. We talked about the properties of waves. We talked about the behavior of waves, and electromagnetic waves were brought up. They're a special type of wave because you do not need, or I should say, not you. There does not need to be any matter present for electromagnetic waves to be able to travel. They can travel through a vacuum. They can travel through empty space uh, which again is why, and I'm giving an example, why sunlight can travel 93 million miles through nothing, but still reach planet Earth. So, what's the basics? What are the basics behind an electromagnetic wave? It's a little confusing, but in a nutshell, uh, let's say you have a little tiny particle right over here where my mouse is. You have an electron, and an electron is going to it's going to vibrate. Some energy is gonna hit it, and it's going to cause it to vibrate. Well, it's just a fundamental law of physics, or a fundamental force of physics called the electromagnetic force. Surrounding this electron, there's going to be both electric fields in red and magnetic fields in blue. And basically, what happens is when an electric field starts to change or starts to move, that in turn makes a magnetic field change at the very same time. So as particles vibrating and the electric field's moving, so is the magnetic field, and they each cause the other to vibrate in a different way. So if you look at this picture here, it's almost like not almost like the electric field is moving up and down in this plane, and then perpendicular to that in the other plane of physical space, you have the magnetic field. But the point is, you don't need particles for this to happen. The energy is being transferred through the up and down motion. I was going to use the word oscillation, but I didn't want to confuse anybody. The constant changing of the electric and magnetic fields. So that's how you can get energy from point A to point B just by something vibrating. Okay. So let me go to what else do I want to talk about? Oh, the speed. I guess we'll go right here. This is This is a an image that we shared with you in all of our Google Classrooms. It might look confusing at first, but I'm going to go through it. I'm not going to go through every section, but little by little. And I don't want to give away too many answers because part of your assignment this week is to do research upon or about the uses of these EM waves, these electromagnetic waves we call them. First off, here are the types of electromagnetic radiation or electromagnetic waves that exist. This particular document, this particular image, has radio waves on the left side and gamma rays on the right. That's not the same for all charts, but this particular chart starts with radio waves on the left. So what does that mean? What's happening? The first type of waves that we're going to discuss are electromagnetic waves is radio waves. They have the longest wavelength. Notice up here, this particular section, as I'm mousing over from left to right, the wavelength of the waves are getting smaller or shorter and shorter and shorter. The waves are getting smaller and smaller and smaller. Keep in mind, what do waves carry? They carry energy. So all of these types are carrying energy, but as you go from left to right and the waves get smaller, they're going to end up carrying more energy because all waves, all electromagnetic waves, I should say, travel at the exact same speed. And I'm going to just type in Google here, speed of light. That is the speed of light. I believe in your book, it's, yeah, on page 341, in the emptiness of space in a vacuum, they round this up. They say that light travels at 300 million meters per second, 3 times 10 to the eighth, right there. 3 times 10 to the eighth meters per second. Light travels extremely, extremely fast. And when it travels through things like air, it actually does slow down just a little bit, and that's in the table on page 341. But please understand, all of these waves travel at the exact same speed. So what does that mean? Imagine you're a person and you're just imagine if you could see all of these waves. We'll talk about that in just a second because we cannot see most of these waves without special tools. Imagine you could see these waves traveling by you at the super fast speed of light, and you were able to count the waves going by you. Well, something like a gamma ray, because it has such a short wavelength, the wave is so short, there are going to be more waves going by you in a given amount of time. Many more waves. And again, waves are carrying energy. So for any unit of time, you're going to get much more energy from waves on this side of the electromagnetic spectrum than on the left-hand side. So over here on the left, very long waves like a radio wave has what we call a very long wavelength, but a very low frequency. This frequency where my mouse is very, very low to the gamma ray section. So again, I mentioned hertz last unit in my last video, but for every second of time, gamma rays would be going by you or into your body 10 to the 20th number of waves every single second because they're so short, and radio waves because they're so long. They would only be 10 to the fourth waves would be going past you or into you every second. So low energy on the left side of the spectrum, high energy on the right side of the spectrum. It's because the wavelength gets shorter and shorter, and the frequency gets longer and longer. Just as a reference, I'm looking at radio waves right here. This right here, this confuses some students or has in the past. This is just kind of showing the the scale of how long the waves are. So a single radio wave, which is 10 to the third meters in wavelength, that's 1,000 meters. That's taller than many buildings. Okay. Um, I guess the last point that I wanted to make is that humans can only see a very, very small section of the entire EM spectrum, the entire electromagnetic spectrum. This section right here, where I'm mousing over, this tiny little section in here, is what we call the visible portion of the spectrum, what we can see with the naked eye. We know that these other types of electromagnetic waves exist, but we simply can't see them without having special tools. I think that pretty much covers it. Again, if anyone has any questions, don't hesitate to email myself or Miss Wood. You know how to contact us. And have a great week. Thanks.